Okay, so this is the Unit 4 study guide. I'm going to try to be fairly quick on this one because I don't want to make a super long video. So hopefully this kind of helps out. So the first part says draw a picture of a wave and label the following parts: origin, amplitude, crest, trough, and wavelength. I'm actually just going to use this wave right here to kind of label that. Okay, so if we look at this line right here, let me actually turn my pin on first. If we look at this middle line right here that goes through it, that is called your origin. Okay, your amplitude is going to be the distance from the middle line to the top of the wave or the bottom of the wave. Okay, so that little distance from the midpoint to the top or bottom, that is called your amplitude. Your crest, that is going to be the top of a wave. And then the bottom of a wave is going to be called a trough. The way I remember that is it looks like half of a cylinder. So that looks like a feeding trough like they use on a farm. Okay, and last thing we need is wavelength. Now this probably causes a lot of confusion, is wavelength. In order to be one full wavelength, you actually have to have one full crest and one full trough. So let me clear up this stuff real quick. Oops, not that one. So let me clear up this out of the way. 1 second. Apparently this is more difficult than I thought. All right, so in order to be one full wave, you have to one full crest and one full trough. So if I start right here at that midpoint, I would go all the way up and all the way down, and it would end right here. So that would be one wavelength right there. Or I could start at the top. I could go down and then all the way back up and then end right there, and that's another wavelength. As long as you have one full up and one full down, then you're good. Okay, so those are the parts of a wave. So now let's actually talk about wavelength and frequency. So in the diagram above, both letters A and B represent the wavelength. Okay, so wavelength. And I'm also going to be referring to wavelength as upside down Y. That's called lambda. So if you see that, that means wavelength. So in B, it says compare letters A and B. Explain how increasing A would affect the energy and frequency. So that means if I went from A to B, if I made my waves longer, how would that affect my energy and frequency? Well, if I made my waves longer, my frequency would have to go down, because if I have a long wave, I can't have as many waves in that period of time. So frequency would go down, and my energy is also going to go down, because the more waves I have in a second, okay, that will be more energy. So if I'm going to make those longer and I'm going to reduce the amount of waves in that time, my energy is going to go down. Now at C it says, so we're basically going backwards now. So if I'm going to go from B to A, so I'm going to go from the B wave to the A wave. Okay, what I'm doing is I'm making my wavelength shorter. Okay, if I make my wavelength shorter, I can have a higher frequency, okay, which is the number of waves, which also is going to increase the amount of energy. Okay, the way I like to remember this is if this was the ocean up here, okay, if I was standing out in the ocean, I'd probably prefer this one right here, this bottom one, B, because it's a little more calm. Okay, you've got 3 waves during that time. I would not want to be floating in the water if I have all those waves right there, because they're more frequent, so therefore there's more energy, which makes it more difficult to stay in that water. Okay, moving down, so answer the electromagnetic radiation EMR questions below. What happens to the wavelength of an EMR wave if you double the frequency? So remember, if I want to double the amount of waves in that time, okay, so if I want to double my frequency, my wavelength would have to go down, okay, because if I want to increase the amount of waves, okay, I'm going to have to shorten those waves, okay, and it's just going to be the opposite. So my wavelength is going to go down by half. Okay, I want to triple the frequency of a radio wave. What specifically should I do to a wavelength? Okay, so if I want to triple the frequency, I'm going to have to reduce that wavelength by a third. Oops, that is not a third, that is a half. So we'll fix that by a third. Okay, now in order to do these next questions, you need to make sure you know your EMR spectrum. So that would be radio. Okay, then micro, so microwaves. Then infrared, so I just abbreviate it IR. Visible light. UV. X-ray. and then gamma. Okay, under visible, it is going to be Roy G. Biv. Those are your colors, so red, orange, yellow, green, blue, indigo, violet. So radio is going to have a long wavelength, nice and calm, long wavelengths, very low frequency, and very low energy, which makes sense. We have radio waves all around us, so we would like them to be low energy. Otherwise, that would be damaging to us. Versus gamma, as you go towards the right, my wavelength is actually going to go down. Okay, it's going to get shorter, which makes my frequency go up, and my energy always goes up as well. Okay, so now what we're going to do is we're going to use that to kind of help us on the next questions. It says, which EMR waves have the shortest wavelength? Well, that's going to be anything towards the right, so gamma is definitely going to be the shortest. Okay, which EMR waves have the highest frequency? That's also going to be gamma. Okay. E, which two types of EMR waves are on the either side of visible light spectrum? So either side of the visible would be IR and then UV. Now, which has longer wavelength? Visible light. Which one has a longer wavelength and which one has a shorter? Okay, so IR is going to be your longer wavelength and UV is going to be your shorter wavelength. So remember that upside down Y or lambda just means wavelength. Which color of visible light has the least energy and longest wavelength? Okay, so as we go to the left, okay, of our EMR spectrum, our energy goes down and our wavelength gets longer. So that means red is going to be our lowest energy but longest wavelength. G says which color of visible light has the most energy and shortest wavelength? That is going to be violet. Rank the gamma rays, radio waves, ultraviolet, and visible light waves in order of increasing wavelength. So increasing wavelength is going to go towards the left. Okay, so I want to start at the right and go towards radio. Okay, so if I did that, okay, gamma would be my shortest wavelength. So I'm going to start with gamma. Okay, then I'm going to go to UV, then visible, and then radio. So radio is going to be the longest of the wavelengths. Okay, I says rank yellow, X-rays, microwaves, and infrared in order of decreasing frequency. So decreasing frequency means longer wavelengths, so that means it's also going to get bigger as you go to the left. So I'm going to start off with the with the most frequency. Okay, the most frequency would be X-ray. Then you have yellow light, because that's part of the visible spectrum. Then you have IR. And then you have micro. So micro would be the longest wavelength, lowest frequency. J, rank red light, violet, orange, and green in order of increasing frequency. So increasing is going to go towards the right. So we're going to go from left to right. Sorry, my apologies. So red is going to be the lowest frequency, then orange, then green, and then violet. Okay, so we're just reading from left to right. Which EMR waves have the highest velocity? This is kind of a trick question. They all travel at the speed of light, and that is the 3.0 times 10 to the 8 meters per second. So radio all the way to gamma, they all travel the exact same speed, which is the speed of light. Now, if you need help memorizing the EMR spectrum, the way we went over it in class is red Martians invade Venus using X-ray guns. So if that kind of helps you out, if you want to come up with your own sentence, that's totally okay. Which EMR waves have the highest energy? That's going to be gamma. So frequency and energy are tied hand in hand. Describe and draw an example of the relationship between the frequency of an EMR wave and its energy. I'm not going to really draw one, but I'll explain the relationship. Is if my frequency goes up, which means the number of waves, my energy is also going to go up. That is called a direct relationship. That means if one goes up, the other one goes up. Now, frequency and wavelength are opposite of each other. If I want my frequency to go up, my wavelength has to go down. That is called an indirect relationship. Okay, so it helps to know those terms. If the frequency of an EMR wave were halved, how would the energy value change? So remember, if frequency goes down, okay, the number of waves goes down, my energy is also going to go down. So remember we talked about the ocean. If you're out there and there's not as many waves, there's not as much energy. Okay, so if frequency goes down, energy has to go down as well. Okay, now we get to do our equations. Okay, so I'm not going to do all these. I'm going to kind of skip around to make sure I hit all the main equations. Okay, so first you have your constants. You have your speed of light right here, which we will give you that. That's the 3.00 times 10 to the 8th meters per second. And we give you Planck's constant. Okay, so don't get too wrapped up. Sorry. Don't get too wrapped up on the units there. That is just the units for Planck's constant. Since we're dealing with joules and frequency, that's why you have joules times seconds. So don't get too wrapped up in that. Okay, you have three equations. You have your first one, which is C equals frequency times wavelength. Okay, so remember F is frequency. Okay, and then upside down Y is your lambda. That's your wavelength. Okay, so you've got to really make sure you know what each one of these stand for or is abbreviated to. Okay, and then you have E equals energy. So pretty much energy and frequency are pretty self-explanatory. E, energy, F, frequency. It's the upside down Y you've got to know that's wavelength. So your first equation is C equals frequency times wavelength. Your second equation is energy equals Planck's constant times frequency. So E equals H times F. And your third equation is energy equals H times C divided by wavelength. So the way I like to do these problems is I like to label what I'm looking for and label what they gave me. That will help you determine which equation to use. So it says find the frequency. So that means I don't know F, so I'm looking for that. Okay, of an EMR photon that has an energy value of 4.19 times 10 to the 18th joules. So I just gave you E. So let's see which equation has E and F. That would be equation number 2. So that'd be E equals H times F. So all I have to do is plug in now. So my E is 4.19 times 10 to the 18th equals H, which is 6.626. Oops, let me go fix that. Times 10 to the negative 34. And wavelength, I don't know. Oh, I'm sorry, frequency, I don't know. So I'm going to just leave it as F. Now, this is where a lot of students get tripped up, is they try to solve these numbers like they're an equation. Like they're trying to solve 4.19 times 10 to the 18th. That's just a really big number. That's like, instead of me writing 16 zeros behind that 9, it's just an abbreviated number. So the way I like to look at this problem is, this is pretty much just like, what if I gave you an example like 6 equals 2x? Okay, 6 would be right here, and then 2 would be right here. Okay, if I want to get x by itself, so x being frequency, I would divide both sides by 2. Okay, so this is the same concept. So let me clear this up for a sec. Okay, so if I want to get f by itself, I'm going to divide both sides by 6.626 times 10 to the negative 34. So both these cancel out. And now I get to bring that over here. So 6.626 times 10 to the negative 34. So all I got to do is take that 4.19 times 10 to the 18th and divide it by h. Just please make sure you use parentheses in your calculator, because if you don't, you can get the wrong answer. Also, on your quiz and test, or just your test, it helps to show us your work, because if you did all this right and then you just did the calculator part wrong, you're going to get most of your credit back. Versus if you don't show us any work and you get the wrong answer, there's not much we can do to help you. So you're going to take that top number divided by the bottom number. Okay, and if we look at our number right here in our problem, it was 4.19. That is 3 sig figs. So my answer should be in 3 sig figs. So in the calculator, I got, so frequency equals 6.32 times 10 to the 51 hertz. So the unit for frequency is hertz, so Hz. And that's your answer right there. B, calculate the frequency of a wave that has a wavelength of 4.15 meters. So that means I am looking for F again, and I gave you wavelength. Okay, so the upside down Y. So I'd see which equation has both of those two. That's going to be equation number 1. So C equals frequency times wavelength. So I'm going to plug in what I know. I already know C, that's 3.00 times 10 to the 8th, equals frequency I don't know. I'm going to leave it as F. And my wavelength is 4.15. So same thing, I'm going to divide both sides by 4.15. Okay, and we should get a frequency of 7.23 times 10 to the 7th hertz. Okay, so let's look at the next one. What is the wavelength of a wave with a frequency of 5.77 times 10 to the 14th hertz? I was given F, and I'm looking for lambda. So I'd see which one has both. So that's going to be C equals frequency times wavelength. So I'm going to do 3.00 times 10 to the 8th equals frequency, which is now I know is that. So it's 5.77 times 10 to the 14th. And wavelength I don't know, so I'm going to leave that as lambda. So I'm going to divide both sides by that 5.77 times 10 to the 14th. And we should get 5.20 times 10 to the negative 7 meters. Okay, so remember wavelength is in meters. So the way I remember that is length meters. Okay, so D, what is the energy? So that means I'm looking for E. Okay, of a wave with a frequency of 4.00 times 10 to the 4th hertz. So I gave you F. So the equation that uses both of those is E equals H times F. So energy I don't know, so I'm going to leave that as E. H is Planck's constant, so that's 6.626 times 10 to the negative 34. Times my frequency, so 4.00 times 10 to the 4th hertz. So all I got to do is just multiply those two. So again, please make sure you're using parentheses. And for energy, I got 2.65 times 10 to the negative 29 joules. So the unit for energy is joules. E, what is the energy? So I'm looking for energy. That's my question mark. Of a photon with a wavelength of 7.67 times 10 to the negative 7 meters. So I gave you lambda, upside down y. So the equation that has both of those is equation number 3. So we're going to have E equals H times C over wavelength. Okay, so what I'm going to do is I'm going to plug that in. So E, I don't know. H is 6.626 times 10 to the negative 34. C is 3.00 times 10 to the 8th. And then wavelength is 7.67 times 10 to the negative 7 meters. Okay, so I'm just going to multiply H times C and then divide it by that bottom number. And I get a value of 2.59 times 10 to the negative 19 joules. Okay, so that's your answer right there. So let me jump down to one real quick. I'm going to jump down to H because some of these are starting to get repetitive. It says, what is the wavelength? So that means I'm looking for lambda. And I gave you 5.6 times 10 to the 23rd joules of energy. So I gave you E. So again, we're going to use equation number 3. So E equals H times C over wavelength. Now, one thing you can do on this equation and this equation only, okay, is if you are looking for something on bottom, which we're looking for that lambda, you can actually switch these two. Okay, you can put E on bottom and then move the lambda over to the left. Okay, so that is a trick only for this equation. Okay, so if you're looking for something on the bottom, you can switch those two. So just please don't switch whenever you want to. It's only when you need that bottom variable. So wavelength, I don't know, so I'm going to leave it like that. H is going to be the 6.626 times 10 to the negative 34. Okay, C is going to be 3.00 times 10 to the 8th. And then my energy can go on bottom, so 5.6 times 10 to the 23rd on bottom. So I'm going to multiply the top two, divide by the bottom, and I get a wavelength of 3.5 times 10 to the negative 49 meters. Okay, so hopefully that kind of helped you out there. Number 5, use the diagrams below to answer the questions. In the electron transition below, is energy being absorbed or released? Okay, so in my class, what I like to talk about is you have an electron that's going from an inner ring or inner energy level to an outer. So the way I remember this, or the way I teach my class, is I think about Halloween and candy. Okay, so if my kids, if they eat candy, okay, so they absorb that energy, the last thing I want them to do is be inside my house right here. Okay, so when they absorb that energy, I want them to go outside to burn the energy. So right now, what's happening is the electron is absorbing energy. When it does that, it jumps to an excited state. So jumps to an excited state. Oops. Okay, so that electron just being energized, it jumps to excited state. Okay, now, which brings me down to my next picture, is once my kids burn that energy, they can come back home. So what that little squiggly arrow means is you're releasing energy. So right now that electron is releasing energy. And it returns to a ground state. So it returns back to home or normal. So it returns to ground state. Okay, so ground state means everything is where it should be. Excited state means an electron absorbed energy and jumped to an outer level. Okay, so let's move here. Complete the following tables. So before I get to this, I want to go down to the periodic table real quick to make sure that you are aware of all your S and P stuff. Okay, so remember you had your S block. Okay, so when we're doing electron configuration or rotation, you have your S block, which is right here. Okay, it has 2 columns, so it can hold 2 electrons. Okay, now helium is a part of that S block, so that would make that 1s2. So helium would make that 1s2. So don't forget helium over there. Okay, then you have your P block, so P block is over here. If you count your columns, you have 6. So this is your P block. So that means it can hold 6 electrons. Then you have your middle block. This is called your D block. Okay, so D block can hold 10 electrons. If you count, there's 10 columns. And then you have your F block down here. Okay, that can hold 14 electrons because there's 14 columns. So make sure when you're doing this, you are reading it like a book. So if I'm trying to get to something like copper, I'm going to have to go through 1s, then 2s, then 2p, then I can go down to the next one, then 3s, then 3p, then 4s. Now this is where you got to be careful. So in order to know the energy levels, okay, S and P will follow these numbers on the left. Okay, so if I look at the first one, that would be 1s. Then the next row would be 2s. Then the next one would be 3s. Same for the P. Okay, boron, carbon, nitrogen, that would be 2p. Aluminum, silicon, phosphorus, that would be 3p, and so forth. D block is always 1 behind. So I think of this as if I have a D in class, I'm slightly behind. So if I'm on energy level 4 right here, I would go from 4s to 3d. So this level right here would be 3d. If I was on 5s, this would be 4d. If I was on 6s, this would be 5d. Okay, so just please make sure you know that D is always 1 behind. Then when you jump across to P, the P block, you go right back up. So it goes 4s. Let me switch this up real quick. Let me do a different color. If I go 4s, then it goes 3d, and then back to 4p. Okay, so that should help you there. Now your F block is going to be 2 behind. So if I have an F in class, that means I'm really behind. So F is going to be 2 behind. So if you look at level 6s right here, okay, you'll notice that this atomic number jumps from 56 to 71. Okay, so you cannot jump to those. You got to go down here first and go through the F block. Now F is going to be 2 behind. So if I was on level 6s, this would be 4F. Then if I went all the way through this, then I can go back and start back up here at 71. So you see how it goes from 70 to 71. Okay, so you got to kind of go through that F detour before you can go back to 5D. So we're going to kind of go through some of these examples. So hopefully that kind of helped clear some of that up. So let's go back up. Okay. Now, these are mostly for when we're doing orbital notation. So orbitals when we do like the arrows. So 1s, 2s, 2p, some p, which we'll go over those in just a second. P can hold 6 electrons, so that's why we have 3 pairs, 3 pairs of 2. So off-balance principle. So our keys are a little more in depth, so this is going to be kind of quick. Off-balance principle is just states that it has to go in order. So it has to go 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d. It just has to go in that order. The reason why is it because those are the lowest. You're ranking these energy levels as far as energy. This would be the lowest energy. Okay, as you add more energy levels, you're adding more energy, because electrons, they don't really like the energy, so they're going to pick the lowest energy level first. So if I look at this, after 3D, it would be 4p. Okay, so 3D is actually a lower energy level than 4p, so that's why it goes from 4s to 3D, then back to 4p. Okay, so basically don't get too wrapped up in that. Is just off-balance principle states it has to go in that order. So if I did something out of order, so say I said 1s and then 2p and then 2s, that would be violating off-balance principle. Now Hund's rule, the way I remember this is spread the hundos, like spread the $100 bills. Okay, that means that electrons have to be spread out. Okay, so if I can spread them out, I'm going to. So if I had something like 2p, okay, I've got 3 energy levels, and say I had 3 electrons to put there. Okay, so the way I think of this is like 3 seats on a bus, and I've got 3 people. Okay, these people are going to spread out because they don't want to be near each other. Okay, so one's going to sit here, one's going to sit here, one's going to sit here. That would be the correct version, is you would spread them out. The wrong version is if I did something like this. So I have my 3 seats, and then I put 2 people in that first seat, and I put 1 in that next, and I leave an open seat. So it's almost like, why would I have an open seat if there's 3 people and 3 seats? So that would be violating Hund's rule right there. Pauli's exclusion principle, the way I remember that's kind of weird, is I think of Pauli as the weird person kind of walking towards you, just because their name is weird. Okay, so Pauli is the weird person. So if Pauli's walking towards me, okay, so arrows would be like my electrons. So if Pauli's walking towards me, I'm going to walk the other way. Okay, so your arrows have to be opposite. So if I did something like this, if I did like an up, up, okay, those electrons are not going to go in the same direction. So that would be violating Pauli's. Now, it does not matter here if you do down then up or up then down. It does not matter which one you start with. That's totally up to you, as long as they're going opposite directions. Because these electrons, they don't like each other, so they're going to spin the opposite way. Okay? Now, going to the next one, we kind of talked about this. S can hold 2 electrons because it's got 2 columns. Now, as far as energy levels go, that's the number on the side of the periodic table you see on the left side. So S starts at 1. Okay, so energy level 1 on, okay, S is going to start that first energy level. P can hold 6 electrons. That is actually going to start on level 2. D can hold 10 electrons. Okay, our first D is actually 3D, so that's going to start at energy level 3. Then F block, F can hold 14 electrons. Okay, and that is going to start, your first F block is 4F, so that's going to start at energy level 4. Okay, now let's look at some examples. I am not going to do all these, but I'll try to do a good amount of them so you kind of get the idea of it. So you got some things to look at. Is first, you need to figure out the number of electrons. Okay, in order to find out the number of electrons an atom should have, is all you have to do is just look at the atomic number. Okay, so like magnesium, if you looked up in the periodic table, it has a number of 12. So it has 12 electrons. Now, electron configuration, that means you get to do the exponents. So like 1s2, 2s2, 2p6, 3s2. Okay, when you're doing the exponents, you can do electron configuration. Orbital notation, if you see orbital notation, that means you have to do the arrows. Okay, so all we're doing is basically just converting those exponents into arrows. So if I look at magnesium, this first one, okay, 1s. So S can hold 2 electrons, remember? So that would actually be 1 pair. So each line I draw means a pair. So if I did 1s2, that means this one's going to be full. So I'm going to do an up arrow and a down arrow. Okay? So my arrows should match the exponent. So if I start 1s2 over here, I should have 2 arrows. Then I'm going to do 2s. I'm going to do 1 line, and that one's full, so I'm going to do 2 arrows. Now 2p, remember 2p can hold 6 electrons, so that's 3 pairs. So I'm going to draw 3 lines. Okay? So I'm going to fill those up. The way I like to fill these up is I like to go ups first and then my downs. If you do that way, it helps make sure that you follow Hund's rule, because it makes you spread them out first before you stack them. So 2p6, okay, then 3s2. So I'm going to draw 3s and then do 2 arrows. Okay, so that's my answer. If you ever want to check yourself, if you add up all these exponents right here, that should add back up to 12 or your atomic number, which it does. Or over here, if I add up all my arrows, that should add back up to 12. So those arrows mean electrons. So if I did something like oxygen, oxygen is number 8. Okay, if I go down here to my periodic table, okay, let me clear some of this up real quick, just to kind of get things out of the way. All right, so I have oxygen right here. So if I'm going to do oxygen, so these are all extended. So extended means you got to start back at level 1. Okay, so I'm going to go through 1s. So this would be 1s. So both hydrogen and helium would be 1s2. Then I got to go through lithium and beryllium. So that's 2s2. Then my next level is 2p, but I don't have to go through all of them. I just got to go 1, 2, 3, 4 to find oxygen. So that would be 2p4. So what I'm going to do is I'm going to come back up here and put those in my answer. So oxygen was 1s2, 2s2, and then 2p4. Okay, so now if you look up here in the instructions, it says ground state. Ground state just means everything should be normal, so we're not having electrons jump around, so don't get too worried about that. You will never have to draw an excited state because we honestly don't know which electrons are going to jump and where. Okay, so electron configuration, that's when you do the exponents. Orbital is when you do the arrows. When you see expanded, expanded means you just have to start back at 1. You have to start at hydrogen. Okay, so I'm going to do 1s, go draw my 2 arrows, then 2s, then draw my 2 arrows, then 2p. Okay, so I'm still going to draw 3 lines. You always draw 3 lines no matter what. So even if you only had 1 arrow, I'm still going to draw those 3 lines. I don't have to use them. Okay, so it's okay to have blank spots. So if I have 4, I'm going to go up, 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 and then down. And that would be my complete answer. Okay, let's do calcium next. So calcium is number 20 on the periodic table. So let's go find calcium. Okay, so let me clear this up again. So we'll start back at 1. So calcium is right here. It's number 20. So I got to get there. So I'm going to start back at hydrogen. So I'm going to go through hydrogen and helium. Okay, let me clear these up. So that'd be 1s2. Then I got to go through lithium and beryllium. So there's 2s2. Then I got to go all the way through 2p. So there's 2p6. Then I got to go through 3s2. So there's 3s2. Then I go all the way through aluminum and argon. Okay, that is 3p6. And then through potassium and calcium, so I got to go through both of those, so that is 4s2. So that would be my answer for electron configuration. So let's bring that back up here. Okay, so calcium was 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2. So I'm going to convert those to orbitals. So I'm going to do 1s, 2 arrows, 2s, 2 arrows, 2p, draw my 3 lines. I'm going to fill all those up. Okay, so there's 6 arrows in there. Then you have 3s with 2 arrows, 3p, I'm going to draw another 3 lines. I'm going to fill all those up. And then I have 4s2. Okay, that is my answer right there. Okay, so what I'm going to do is I'm going to jump to copper because I want to do one that has a D block. So copper down here. Copper is number 29 on your periodic table. So let's go find that one. Apologies for the coughing. So let me clear some of this stuff up. All right, so copper is right here. It's number 29. So I'm going to do expanded. So I'm going to start from hydrogen. So I got to go through hydrogen and helium. So there's 1s2. Then I got to go through 3 and 4. There's 2s2. I'm going to go through the next one. That's 2p6. Then I got to go through 3s2. then 3p6, then 4s2. Now, that's where you gotta be careful. Remember, D block is always one behind, so this is actually going to be 3D. And then I'm going to count to copper. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 3D9. Okay, so let's go back up here. So copper, remember, so that was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d9. So let's convert ours to orbital. So I'm going to draw 1s, 2 arrows, 2s, 2 arrows, 2p, I'm going to draw my 3 lines. 1, 2, 3, 4, 5, 6. That one's full. 3s, 2 arrows, 3p, draw my 3 lines. I'm going to fill all those up. Then you have 4s with 2 arrows. Now 3D, remember D can hold 10 electrons. So I'm actually going to draw 3D, and I'm going to draw 5 lines because 10 divided by 2 is 5 pairs. Okay, so I need 9 of them. So I'm going to start with the up. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means that last box is just going to have 1 arrow, and so that is okay. And that would be your answer for that. So let's go actually jump down to the next part. Okay, our noble gas shortcut. So now we actually get to do a little bit of a shortcut. So we're still going to do electron configuration, so it means exponents, and we're still going to do orbital. So let's talk about our noble gases. Okay, so let me clear some of this up. Okay, so noble gases, those are going to be your last column right here. Okay, so helium down to radon, those are your noble gases. So what you're going to do is you're going to treat those like a check mark or a checkpoint that you get to start from. So if we say noble gas, you get to start from that noble gas instead of starting back at square one, which is hydrogen. Now, the trick to doing this is you have to start at the last noble gas. So if I had something like arsenic, okay, number 33, the last noble gas before that would be argon. So that means you get to start at argon. If I had something like phosphorus, the last noble gas would be neon. If I had something like antimony, Sb, my last noble gas would be krypton. Okay, so you always have to start at the one before the element you're trying to get to. Okay, so let's go back up and see what our examples are. Okay, so let's start off with something simple. So we've got lithium. So lithium is actually number 3 on your periodic table. Okay, so we're going to figure out what is the noble gas before lithium. Let me clear some of this up real quick. Okay, so if lithium is right here, number 3, the last noble gas before that would be helium. Okay, so let me clear up this top part before we write it out. So what you're going to do is, once you know that noble gas, you're going to write that noble gas in brackets. So I'm going to put helium in brackets. And then you get to start at level 2. Now, lithium is on 2s, and it's on the first one. So this is just going to be 2s1. Okay, so that would actually be your electron configuration answer for lithium. So we're going to go back up and put that here. So this would be helium in brackets, and then 2s1. Now, noble gas orbital notation is just the same thing. We're still going to write helium. Now, instead of 2s1, I'm just going to put 2s with a line above it, and I'm just going to put 1 arrow there. That's it. That's your answer. Okay, so let's do silicone. So silicone's number 14. Let's go back down here. So silicone is number 14 right here. So my last noble gas before silicone is neon. So that means I'm going to write neon in brackets. Okay, then I'm going to go down here to the next level. I'm going to start at sodium and magnesium. So I got to go through 3s2. And now I'm in 3p, but I'm only going to go 2 in. So that would be 3p2. And that would be your answer for electron configuration. So let's put that back up here. Okay, so silicon, that was Ne in brackets, 3s2, 3p2. Now I'm going to put that in orbital notation, so I'm still going to write neon in brackets. I'm going to draw 3s with 2 arrows. I'm going to draw 3p with three boxes, but I only have 2 electrons, so all I'm going to do is just up, up. So it is okay that you have an empty space. As long as you're not stacking those 2 in the first box, that is okay. So you can have an empty spot, so don't feel like you have to fill those up. Let's do rubidium. Okay, so rubidium right here is number 37. So let's go back down here. Clear this up. Okay, so rubidium is number 37 right there. So the last noble gas before rubidium, that would be krypton. So I would write krypton in brackets. And then your next level is actually 5s. But I only went 1 in, so that's going to be 5s1. So that'd be your answer right there. So let's put that back up there. Okay, so it would be krypton in brackets and then 5s1. Okay, so I'll do the same thing over here, krypton in brackets, and then I would do 5s with just 1 arrow. Okay, let's do one more. Let's do silver. Okay, so I'm going to do silver, which is number 47, down here at the bottom. Man. Okay, so let's find silver. Silver is number 47 right here. So the last noble gas before that is krypton again. So we're going to write krypton in brackets. Then I'm going to go down here to 5s2. I'm going to go through both of those. So that's 5s2. Now this D block, so it's behind. So this is actually technically 4D. Now count all the way to silver, which would be 9. So 4D9. That would be your answer right there. Okay, so my answer for silver was krypton in brackets, 5s2, 4d9. Now we're going to put those in orbitals, so krypton in brackets, 5s with 2 arrows. And then 4d, remember where D can hold 5 pairs, so that's 5 lines. And I've got 9 of them, so I'm going to go up, 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 so that's 5. And then down, 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 down. That makes 9. Okay, so that's your answer right there. Number 15, don't get too wrapped up in this. This is just kind of transitioning you into the next unit. Remember, ions, those were if you lost or gained electrons. So remember, if it was a positive 2, that was actually you lost 2 electrons. So instead of 12 electrons, this would actually be 10. Okay, because you lost 10 electrons. So what you would do for your electron configuration would just be 1s2, 2s2, 2p6. So these numbers right here should just add up to 10. Okay, so you're just going to do that until you get to the number of electrons you have. Okay, and then again, orbital notation, that's stuff we just went over. So that would be 1s, 2 arrows, 2s, 2 arrows, and then 2p with 6 arrows. So I looked at nitrogen. Nitrogen on the periodic table is actually number 7. Okay, so it would normally be 7 electrons, but if you see this -3, that means you add 3 electrons. So it would actually be 10. So it's the same thing as Mg plus 2. So it would just be the same thing, 1s2, 2s2, 2p6. Okay, and your orbital notation would just look the same. So again, don't get too wrapped up in these. Honestly, we're probably not even going to quiz on this or test on this in this unit. This is just kind of help transition you to the next unit. Now here, this is the easy part. This is where you just got to find out where these elements are. So if I've got 1s2, 2s2, 2p5, there's 2 ways you can do this. Is one, if you just add up all these numbers, so 2 plus 2 plus 5, that gives me 9. Okay, so if you look up number 9 on the periodic table, okay, that is fluorine. Okay, Or if you know the periodic table well enough, where you know where 2p5 is, you can honestly forget about 1s2 and 2s2 and just find 2p5. So like if I came down here to this one right here, if I add up all those electrons, so 2 plus 2 plus 6 gives me 10, plus 2 plus 6 gives me 18, plus 2 gives me 20, plus 10 gives me 30. Okay, so if I did that, 30 would be zinc. And then your abbreviation would just be ZN. Or you could just figure out what is 3D10, and you could find out there. So there's two ways you can do that. So that should probably be the fairly easier part. So I do want to talk about the bottom two. You have xenon, so this one right here. Okay, 5d6. Now, this can be a little difficult. Is if you want to do the counting part, you would need to figure out what would be the number of krypton, xenon, or radon. Okay, so xenon is number 54. So where that says XE, that means you have to start at 54. So 54 plus 2 plus 14 plus 6. Okay, and that would give you osmium. Okay, and the abbreviation for that would be OS. Okay, or we can figure out where 5d6 is. So if I go down here, let me clear this up. Okay, so 5d6. Okay, so this would be your 5d block right here. So 1, 2, 3, 4, 5, 6, and I get osmium right there. Okay, so just be careful with that F block. So like on the bottom one, it says 7s2, 5f11. So if I go down here, this is level 7s2 right here. Okay, then it jumps down here to the bottom section. The way you can follow that is if you look, you're at 88, and down here you're at 89. So you have to go in order. Okay, so 5f11, so I would count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that would give you Einsteinium. Okay, so my element would be Einsteinium. Okay, the abbreviation is ES. Now this last part, don't worry too much about the ion part, but I'm going to explain it all. So ground state just means everything is where it should be. There's nothing out of order. There's no extra electrons. So if I looked up potassium on the periodic table, potassium is number 19. Okay, so first I'm going to check, is everything in order? So 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. All that adds up to 19. So everything's good. Nothing's out of order. Nothing's out of place. All the electrons are there. So that means ground state. Ground state just means everything's nice and good. Okay. Now, if I have something like over here, sulfur, if you look closely, you have 1s1 and then 4p1. So that normally that 1s1 should be full. If you moved on to 2s2 and 2p5, 1s1 should actually be 1s2. But in this case, one of those electrons got energized and jumped to that 4p. Okay, so this is what we call excited state, is when you have a random electron leave one of those main orbitals that we've been talking about and just jump to a random one. Okay, so that'd be excited state. So if I look at this, so H, I have cesium, I have Xe, and then 6p1. Okay, well if I looked at the periodic table, after Xc, after xenon, it should be 6s, not 6p. So that means one of those electrons got excited and jumped to 6p, so that would be excited. Now, ions, don't worry about this too much, is you would just have to look at the number of electrons. So if you looked up chlorine on the periodic table, that would be number 17. So if I add up my electrons, 2 plus 2 plus 6 plus 2 plus 6, that's actually 18. So that means my electrons are off of where I should be. So that means I actually gain an electron. So that would actually be Cl with a -1. Okay, so that would actually be an ion. Okay, if I looked at calcium on the next one, calcium is normally 20. So 2 plus 2 plus 6 plus 2 plus 6 is 18 again. So if you notice, my electrons are off again, so that is an ion. And that would be technically Ca with a +2. But again, don't get too wrapped up in ions because that's going to be on the next unit. Okay, but I would know the difference between ground state, which means everything's nice and normal, and excited state, which means something jumped to another level. So hopefully that video kind of helped you out. If you need anything, just let us know.